Welcome to The Explainer. Today, we're jumping right into one of the most notorious trick questions you'll ever hear in a machine learning interview. It's a scenario that actually exposes a huge blind spot in how we typically look at AI performance. And honestly, once you understand this, it's going to completely change how you evaluate the systems you rely on every single day. So, picture this. A colleague runs up to you, practically buzzing with excitement, right? They tell you their brand new machine learning model just hit a 95% accuracy rate on the test set. And they ask, should we be happy with this? Now, most of us would instantly pop the champagne for a massive number like that. 95%? It sounds absolutely incredible. It kind of implies the system is practically flawless, nailing it almost every single time. It's basically an A+ in any normal context. But here is where the data context changes absolutely everything. What if your data set is super imbalanced? Let's say you're predicting IT incidents. Out of 10,000 historical tickets, 9,500 are just totally normal, low-priority issues. And only 500 of them are those critical, drop-everything-you're-doing P1 emergencies. Here's the kicker. If you have a super simple, let's call it a lazy machine learning model that just decides to predict every single incident is normal, and it literally never flags a single P1 emergency at all, well, it still technically guessed correctly for 9,500 out of those 10,000 incidents. It hit exactly 95% accuracy while being completely and utterly useless. This is what we call the 95% accuracy trap. So the real answer to your colleague is, well, it depends, because 95% accuracy can actually be incredibly misleading. Making machines learn, the foundations. So if we actually want to catch those hidden emergencies, we first need to quickly clear up some jargon. Artificial intelligence, or AI, is just the broad term for any technique that makes a machine act smart. Machine learning, or ML, is a specific slice of that. Instead of us manually writing out rigid rules, like if CPU is over 90%, raise an alert, we just feed thousands of past examples into the system so it can figure out the patterns all on its own. Deep learning takes us further using complex neural networks, and generative AI, like ChatGPT, uses those networks to create brand new content. A great memory trick for this: every ML is AI, but not every AI is ML. Now, to teach these models to actually spot a real P1 emergency, we don't just dump all our data in at once. We have to split it up. Usually, we use about 70% as training data. Think of this like a student studying past exam questions. Then, 15% is validation data, which we use to fine-tune the model, kind of like taking mock tests. Finally, that last 15% is our test data. That's the final exam, and it's strictly saved for the very end to measure how the model truly performs. We split the data like this to avoid two massive pitfalls. The first is overfitting. This is where the model essentially just memorizes the training data, including all the random noise. Imagine an automated root cause analysis model that perfectly memorizes 920 past incidents, but totally freezes up the second it sees a new one. The second trap is underfitting. This happens when the model is just way too simple. Remember our 95% accuracy trap model that just lazily predicted all incidents are normal? Yeah, that's underfitting. It completely failed to learn the actual underlying patterns. Bias versus variance, the trade-off. This actually brings up a concept that interviewers absolutely love asking about, and it's best explained with an archery analogy. Bias is the error from making wrong assumptions. So high bias means your model is underfitting. It consistently hits the exact same wrong spot on the target. Variance, on the other hand, is the error from being way too sensitive to tiny changes in the data. High variance means your model is overfitting, so your errors are just scattered randomly all over the place. Our ultimate goal? Low bias and low variance. We want to consistently hit that bullseye, meaning our model generalizes perfectly to brand new unseen IT incidents. The ML Toolbox, algorithms for the job. Now, to actually hit that bullseye, we have specific algorithms for specific jobs. Linear regression is used when we want to predict continuous numbers. It finds the best straight line through a bunch of data points, which is absolutely perfect for predicting exactly how many minutes an incident will take to resolve. But hey, here's a really fun interview trick. Despite the name, logistic regression is actually a classification algorithm. It predicts a probability between 0 and 1. So it's exactly the tool you'd reach for to predict a simple yes or no, like whether or not an incident is going to breach its service level agreement. Another tool we can use is a decision tree. These are incredibly intuitive because they just ask a series of simple yes or no questions. The catch? A single tree is notoriously prone to overfitting. To fix that, we upgrade to a random forest. This uses a clever technique called ensemble learning, where we build hundreds of individual decision trees on random samples of our data, and then we literally let them vote to give us the final answer. It dramatically cuts down on overfitting and handles huge data sets beautifully. Solving the mystery beyond raw accuracy. So back to our initial mystery. This is where the magic metric called recall steps in. Look, in incident prediction, missing a real P1 emergency is infinitely worse than accidentally triggering a false alarm, right? Recall measures exactly that. Out of all the actual critical emergencies that really happened, what percentage did our models successfully catch? Because of this, the ultimate answer to that 95% accuracy trick question is to demand a look way beyond raw accuracy. You absolutely have to check the precision, the recall, and the F1 score, which is a metric that balances the two. If a system is bragging about 95% accuracy but has a recall of 0% for critical emergencies, well, you instantly know that model is taking the easy way out and is completely useless for your actual operations. Surviving the real world, ML in production. This brings us to MLOps, or machine learning operations. Building a great model is one thing, but getting it to survive out in the wild is another beast entirely. Just like incident managers handle P1 emergencies in the IT world, MLOps engineers are the ones managing machine learning models in live production environments. They make sure the models actually perform, they spot when things start to degrade, and they fix issues rapidly. Every single real-world project follows a very specific end-to-end pipeline. Take a real automated root cause analysis system, for example. First, you'd collect a massive amount of data, maybe over 44,000 ServiceNow incidents. Then you pre-process all of it to clean out the junk and duplicates. Next is feature engineering, where you might build new text fields. After that, you train your model, perhaps using vector databases and large language models, evaluate your metrics, and finally deploy the whole thing via an API on cloud infrastructure. To make sure these models run perfectly everywhere, from a developer's laptop to live production, we usually package them inside Docker containers. From there, you basically have three main choices for deployment. There's batch prediction, which runs on a set schedule, like predicting tomorrow's SLA breaches every night at midnight. There's a real-time API, where a web request gets an instant prediction the second a new instance is raised. Or you can do edge deployment, where the model runs completely offline, directly on an IoT device or smartphone. But watch out, because here is exactly where that 95% accuracy trap can sneak right back up on you. It's called model drift. See, a model trained on historical data naturally assumes the future is going to look exactly like the past. But what if you train a model strictly on English IT tickets, and then 3 months later, a global expansion suddenly introduces tickets written in Spanish or German? The fundamental distribution of your input data just shifted. We call this data drift, and when it happens, your once highly accurate model is going to degrade, and fast. To survive this kind of drift, MLOps goes a step further than traditional software engineering. It doesn't just use continuous integration and continuous deployment to test and release code. It introduces CT, continuous training. Using tools like Jenkins or GitHub Actions, engineers build pipelines to automatically monitor incoming data. The second they detect drift happening, the system automatically retrains the model with fresh data to bump its recall and precision right back up to where they need to be. So, as you can see, it is surprisingly easy for an algorithm to look absolutely perfect on paper while failing completely in practice. And we've seen how MLOps is the safety net that prevents those failures in the real world. The very next time a vendor or even a colleague tries to sell you on a shiny new AI system that boasts perfectly high accuracy, just stop and ask yourself, what is the 95% trap they aren't telling you about? Are they actually catching the critical issues or just lazily predicting the normal ones? Keep that question in your back pocket, and I guarantee you'll never look at machine learning metrics the same way again.